Hi, and welcome to High School Hacking. I've been really busy, but I've got a lot of updates for you. In this video, we'll talk about how a jet engine works, talk a bit about the design choices I made, and finally talk about how everything comes together. Let's get started. So how does a jet engine work? Essentially, the point is we push air back as fast as possible. Pause here for more information. We can do this using a heating element or a combustion element. Essentially, if we increase the temperature of the air, then it's going to expand, and when it expands, it increases in velocity out the back. To maximize the efficiency of our combustion chamber, we want to have as much air in as possible. Because the more air we have in, the more fuel we can react with the air, and so the higher the temperature in the combustion chamber. To add air in, we can use what's called a compressor. We essentially pull air and we compress air to a higher pressure, which means we have more oxygen, which means we have more explosion, which means we have higher temperature. That's good. Now, how do we power this compressor? Well, we could use an electric motor, but then we have what's called an electric engine. However, this is less good, it's not self-sustainable. Essentially, we have a separate set of batteries and motors, and that's kind of a mess. So instead, I am using what's called a turbine. And the hot air, as it expands outwards through the back, pushes against the turbine, which spins the turbine, which spins the compressor. All that's left to do is do a lot of testing. Using the test setup I built in the last video, I tested about 20 different prototypes. My main conclusion was that height didn't matter a huge amount. Taller led to a bit more performance, but not much. Next was angle. Essentially, the steeper the angle, the worse it was. Steeper being closer to the straight vertical. This kind of makes intuitive sense, but at least it's shown in data. And finally, more blades. In general, more blades look better. So I packed as many blades as I could. You can see in the final design, I have blades within the blades just to maximize the blade count. Then, of course, there is the second stage of the compressor. This one's a bit more complicated, so it depended a huge amount on the stator I had. I tested 4 or 5 different versions before I realized it was the stator that was the problem. So finally, I was able to get something where both the stator and the blades had the right angle. This was a key problem that was hard with the second stage. We need a combustion chamber. Simple, right? We push in some fuel and then we ignite it. It's done. But unfortunately, it's not that simple. Even just something like fuel is complex. Like what I'm debating kind of between butane and propane and ethanol. In the end, I think when you go with butane, honestly just because it's easier to get. But either of the others would be a good option. Then there's obviously ignition. There's kind of 2 main options for ignition. One is to use what's actually meant to be used of a spark plug, but the other option is to just use an arc lighter. These are not really meant for the temperature, but they're just so much easier to get. So I'm not sure. Then there's the problem of flame out. If we put our injector right on the other side of our compressor, it won't work at all. The cold air coming in will cool down the combustion chamber to below the minimum temperature and it's just gonna flame out. So of course we need a combustion tube to hold the combustion in, and you can have holes in this tube to let oxygen in. And then there's the whole problem, where do you put the holes? And also this is just gonna be experimentation. We're gonna start with less holes and drill more as we go until we get to the point where it runs smoothly. The next part is the turbine. This is essentially impossible to test because you can't get the temperatures and pressures that we're going to get in the engine. And yes, I can see all of you are streaming CFD, but I have a Mac, so I can't really test any of it. And either way, CFD is kind of boring. So I kind of made something that looks right and we'll test it later. The final part we're going to talk about is the shafts. This connects the compressor to the combustion chamber. This is made out of 3mm stainless steel because that's kind of what I had. The one problem with this though is it probably will melt given enough time. To stop it from melting, I created a sheath that essentially goes in the combustion chamber and covers the shafts. This increases the thermal mass of the whole thing, which means it'll take longer to melt. It will still melt eventually, but I'm not running this for hours, so that's fine. The sheath also has a secondary purpose of deflecting the air around the bearings and out into the stators for the turbine. Now it's probably a good time then to talk a tiny bit about safety. The engine operates like 10,000 RPM and about 1,000 degrees Celsius. If that doesn't scare you, Google uncontained engine failure. Those are really scary. You do not want to be anywhere near this thing. So to protect from this, I built essentially a 3-sided box, like an enclosure around it. So even if something does explode, if there is an RUD, then the shrapnel will fly into the box down at my eyes. Then of course there's also the issue of a flashback event. Essentially a flashback event is when the combustion goes up the tube and into the can, which explodes everything. Pretty awesome videos I think on YouTube of this also. You really want to avoid that at all costs, and there's a couple other safety measures you can take, but aside from that, I'm just to be like 20 or 30 meters away from the engine when it runs, so that if there is such an event, I won't be dead. Now that we're done with that, let's talk a tiny bit about CAT. This is the model, which is going to be exciting, all there. I should do a quick note on materials. Last time we left that, essentially I was debating between a couple materials. I've decided now. Essentially, we're going to do a mix of CNC steel and 3D printed steel. The 3D printed steel for the complex pieces and CNC steel for the simpler pieces. I was talking to a bunch of manufacturers and they just wouldn't do any of the blade designs. I can't imagine why, so instead we're 3D printing that. That means if places are 3D printed, need to be as easy as possible because those 3D printed parts are about 4 times more expensive than any of the other parts. The only hard part of the design really was the bearings. I mean, first of all, you have to protect the bearings from the really hot throws of air. I mean, we talked about this a bit in the sheet, but that kind of redirects the air around the bearings. But then there's also what's keeping everything in line, like what's keeping everything attached to the rod and then keeping the rod from moving back and forth. This is first of all where the clamps come in, and second of all where all of the thrust bearings come in. Essentially, we line everything up with thrust bearings. But then we have another problem. The steel increased by 3 to 4 millimeters in size over the length of the sheath. And so we have to also account for this, and it leads to a huge mess of tolerances. Let's go back in before it starts raining too much. This is a recent model I showed at my exhibition. By the way, thanks for everyone for coming out there. It was really awesome to meet some of you. So it kind of shows how this works. This is kind of an open model, so you can see the part. This is a compressor here. It pulls the air in, as we talked about. This is the combustion chamber. We're kind of missing the combustion tube. It's in the center here. And then finally, this is a turbine. So thanks for watching. That's going to be it. Next video, we're going to unbox the parts and we're going to build the whole thing.